Now we can do some numericals relating self-induction, mutual induction and AC generator. First question, what is the self-inductance of a coil in which the magnetic flux of 40 milliweber is produced when 2 ampere current flows through it? Here what are the values given? Magnetic flux is given. Magnetic flux is represented by phi b. Phi b equal to 40 milliweber. We can convert to Weber. 40 into 10 raised to minus 3. Weber is the SI unit of magnetic flux. Then current is given by, what is the current? 2 ampere. Clear? Now there is a direct formula. Magnetic flux and current and self-induction are related by magnetic flux phi b is equal to Li. Isn't it? Self-inductance L equal to phi b divided by I. Direct question. Phi b is 40 into 10 raised to minus 3 divided by current is equal to 2. Okay, so it is 20 into 10 raised to minus 3. Self-inductance was, what is its SI unit? Henry. So 20 into 10 raised to minus 3 Henry. Now next question, an air-cooled solenoid with length 30 centimeter, area of cross section 25 centimeter square, number of turns 500, carrying a current of 2.5 ampere. The current is switched off, suddenly switched off in a brief time 10 raised to minus 3 seconds. How much is the average back EMF induced across the ends of the open switch in the circuit? Back EMF is the EMF, induced EMF. Okay. Now, the air-cooled solenoid with length, what are the values given here? Length is equal to 30 centimeter. You can convert to meter. 30 into 10 raised to minus 2 meter. Area of cross section is 25 centimeter square. Area of cross section capital A equals 25 centimeter square. You can convert to meter. 25 into 10 raised to minus 4. Isn't it? 10 raised to minus 2 the whole square. 10 raised to minus 4 meter square. Number of turns is equal to 500. Carrying a current of 2.5. So initially current is 2.5 ampere. So I is equal to 2.5 ampere. Clear? What is the change in current when the current is suddenly switched off? In a brief time 10 raised to minus 3. What is the change in current? We can write change in current is 0 minus 2.5. Isn't it, children? So current, initially the current is 2.5. After some time the current is switched off. Okay, so current is switched off so that the current becomes 0. So what is the change in current? Final minus initial, that is minus 2.5 ampere is the change in current. What is the corresponding time? That is 10 raised to minus 3 seconds. These are the values given. Okay, length, area of cross section, number of turns, change in current and change in time. We have induced EMF E equals minus d phi b divided by dt. According to Lenz's law, E equal to minus d phi b divided by dt. So this can be written as is equal to minus d by dt of what is phi b, since it is self-induction Li. So it can be written as minus L into di divided by dt. Okay, children, what is L? L is called as self-inductance. And what is the value of self-inductance? L equals mu 0 n square A divided by L. Since capital N is given, we can use the formula L equal to mu 0 n square A divided by L. We can substitute mu 0 4 pi into 10 raised to minus 7. Number of turns 500 square. Area of cross section is 25 into 10 raised to minus 4 divided by what is the length? Length is 30 into 10 raised to minus 2. After simplification is equal to 2.61 into 10 raised to minus 3 Henry. Self-inductance SI unit is Henry. After simplification, we will get the answer as 2.61 into 10 raised to minus 3 Henry. Now, EMF, we have EMF equal to minus L into di by dt, no? So, minus L, what is L? 2.61 into 10 raised to minus 3 into di. What is di here? Change in current is minus 2.5. So, minus 2.5 divided by what is time? 10 raised to minus 3. Negative become positive. So, final answer is 6.525 volt. Okay, 2.61 into 2.5, it is 6.525 volt. So, that is the induced EMF. Clear? Now move on to third question. A plot of magnetic flux phi versus current I is shown for two inductors capital A and capital B, which has larger value of self-inductance. So here graph is given, current is plotted along the x-axis and magnetic flux along the y-axis for two inductors having inductance capital A and capital B. So which is greater, which has higher value of self-inductance? That is the question. So we can redraw the graph. Here, keeping current a constant, draw a perpendicular like this, so that it touches the first line A, and here it touches the second line B. Here this is the magnetic flux corresponding to A, let it is phi A. This is magnetic flux corresponding to B, therefore it is phi B. Okay, so here which magnetic flux is given from the graph itself? It is given that phi A is greater than phi B. Magnetic flux corresponding to A is greater than magnetic flux corresponding to B. And we have the formula magnetic flux is equal to phi equal to Li, isn't it? So as magnetic flux increases, what happens to self-inductance? Self-inductance will be greater because current is kept constant, no? So for both A and B, I is kept constant. So as magnetic flux increases is greater for A and self-inductance will be greater for A. So since magnetic flux for A is greater than the magnetic flux of B, self-inductance of A is greater than self-inductance of B. So the question is, which has larger value of self-inductance? A has larger value of self-inductance. Larger value of self-inductance. Okay children? Question. A current is induced in coil C1 due to motion of current carrying coil C2. Write any two ways by which a large deflection can be obtained in the galvanometer. Suggest an alternative device to demonstrate the induced current in place of galvanometer. So this is the coil C1, here this is coil C2. So current is induced in coil C1 due to the motion of current carrying coil C2. If the coil is moved towards to the coil C1, current is induced, which can be detected by using the galvanometer. Now the question is, write any two ways by which larger deflection can be obtained in the galvanometer. So when this coil C2 is moved towards coil C1, what happens? Magnetic flux varies. Magnetic flux varies and EMF is induced, and because of that induced EMF, galvanometer shows the momentary deflection. That is called electromagnetic induction. So write any two ways by which larger deflection can be obtained. So how will you increase the deflection in the galvanometer? Deflection in the galvanometer can be increased by, first method is by increase the voltage in the battery. Okay, by replacing this coil, by replacing this battery by a higher voltage. Okay, connect the coil to a powerful battery. If a powerful battery is connected here, current changes. Current increases means what happens? Magnetic flux varies and hence induced EMF will be greater, and because of that greater induced current, galvanometer shows greater deflection. So first one, by using a battery of greater power, okay, or by connecting the coil C2 to a powerful battery. That is the first method. Second one, C2 is moved towards C1 with a greater velocity. Okay, so if C2 is moved towards C1 with a greater velocity, then also what happens? Magnetic flux varies at a greater rate and hence EMF induced at a greater rate, and the galvanometer shows maximum deflection. So move the arrangement rapidly towards the coil C1, then also galvanometer deflection can be increased. Any other method children? Also, if you increase the magnetic field, how will you increase the magnetic field in C2? By placing a softened core. By placing a softened core in C2. Okay, softened core in C2, what happens? Magnetic field increases. Magnetic field increases, then again magnetic flux varies and hence EMF will be induced at a greater rate. So there are three methods by which galvanometer deflection can be increased. So first one, use softened core inside coil C2. Connect C2 to a powerful battery, moving the coil C2 rapidly towards C1. Now second one, suggest an alternative device to demonstrate the induced current in place of galvanometer. So instead of galvanometer, in order to detect the presence of induced current, we can use a small torch bulb also. Okay, so the glowness of the torch bulb indicates that there is induced current. So instead of galvanometer, what is the other device which can be used? That is torch bulb. So second answer is replace the galvanometer by a small torch bulb. Okay children. Obtain the expression for magnetic energy stored in a solenoid in terms of magnetic field, area, length of the solenoid. How does the magnetic energy per unit volume compare with the electric energy per unit volume in a capacitor? So we have to derive the formula for magnetic energy stored in a solenoid in terms of magnetic field, area and length. We know the energy stored in a solenoid, the magnetic energy stored in a solenoid is given by UB equal to, what is the energy stored in a solenoid? We have half Li square. Okay, energy stored in a solenoid or energy stored in an inductor is in the form of magnetic energy, and the energy value is half Li square, where L represents the inductance and I represents the current. And we have L. What is the formula for L? Self-inductance of a solenoid is mu 0 n square Al, where small n represents the number of turns per unit length. And what is the magnetic field inside the solenoid? And from this I can be written as, what is the I? B divided by mu 0 n. So we have the formula energy is equal to half Li square, L is mu 0 n square Al, and the current I is B divided by mu 0 n, where B represents the magnetic field inside the current carrying solenoid. You can substitute UB energy equal to half L. What is L? Mu 0 n square Al. Okay, and what is current I? The current I is equal to B divided by mu 0 n the whole square. We can simplify it. It is given by n square get cancelled, and it can be written as B square Al divided by 2 mu 0. Okay, so B square Al divided by 2 mu 0. This is the energy stored in an inductor in terms of magnetic field, area and length. Second part is, how does the magnetic energy per unit volume compare with electric energy per unit volume in a capacitor? We have energy per unit volume. Energy per unit volume is called energy density. So magnetic energy density is energy divided by volume. Energy density is usually represented by small letter u. So energy, what is the energy? B square Al divided by 2 mu 0, the whole divided by, what is the volume? Volume of the solenoid is Al. Al and Al get cancelled. So magnetic energy per unit volume or magnetic energy density is half mu 0 B square, or B square divided by 2 mu 0. In the second chapter we have studied electric energy density. Energy density in a capacitor is half epsilon 0 E square. So this is the electric energy density in a capacitor. This is the magnetic energy density in a solenoid or an inductor, and the magnetic energy density is B square divided by 2 mu 0, and electric energy density is half epsilon 0 E square. Okay children? A pair of adjacent coils has mutual inductance of 1.5 Henry. If the current in one coil changes from 0 to 20 ampere in 0.5 second, what is the change in flux linked with the other coil? Here the given value is mutual inductance of 1.5 Henry. So M equal to 1.5 Henry given. Change in current changes from 0 to 20. So what is the change in current? 20 minus 0, that is 20 ampere. Change in time equal to 0.5 second. We have to find out the change in magnetic flux. Okay, and we have the direct relation induced EMF E equal to minus d phi b divided by dt is equal to, from using the mutual inductance formula, what is that value? Minus m into di divided by dt. Okay, because phi b equal to mi. So using that formula, this EMF can be written as minus d phi b by dt equal to minus m into di by dt. Clear? Here dt and dt get cancelled. So what is d phi b? D phi b equal to m into di. We have to find out the change in magnetic flux, isn't it? So what is m given? M is 1.5. What is the change in current? 20. Okay. So answer is equal to 30. Magnetic flux unit is Weber. So answer is 30 Weber. The mutual inductance of a pair of coils change when number 1, distance between the two coils is increased, number of turns in each coil is decreased, thin iron sheet is placed between the two coils, other factors remaining the same. Justify your answer. How does the mutual inductance vary? So we have the formula for mutual inductance. What is the formula for mutual inductance? M equals mu 0 N1 N2 pi r square into L. This is the formula, or area into L. Mu 0 N1 N2 pi r square L. Okay, N1 and N2 are the number of turns per unit length. R represents the radius of the inner coil and L represents the length. Okay. Now, what happens if the distance between the two coils is increased? If two coils, the distance between the two coils is increased, what happens to mutual inductance? So, if the distance between the two coils is increased, what happens to the flux passing through the coil? Magnetic flux passing through the coil is decreased because distance is increased, no? So, magnetic flux passing through the coil decreases and hence mutual inductance decreases. So, answer is like this: when distance between the two coils is increased, flux passing from one coil to another decreases and hence mutual inductance decreases. Clear? Now, the second one, number of turns in each coil is decreased. Number of turns decreases means number of turns per unit length also decreases. So, number of turns per unit length decreases means what happens to mutual inductance? That also decreases. Okay. So, if number of turns decreases, mutual inductance decreases. Then third one, a thin iron sheet is placed between the two coils, other factors remaining the same. If thin iron sheet is placed means we have the mutual inductance formula M equals mu 0 N1 N2 pi r square into L, or pi r square means area into length. With iron sheet, with thin iron sheet, how will you write the mutual inductance? M equal to mu 0 mu r N1 N2 pi r square into L. Okay, mu r is always greater than 1. So, if an iron sheet is placed, what happens? Mu r increases and hence mutual inductance increases. Okay, so mutual inductance increases. This is the reason. So, when an iron sheet is placed, mutual inductance depends on mu r. It is directly proportional to mu r and mu r is always greater than 1 and hence mutual inductance increases. Okay. Kamala pedals a stationary bicycle. The pedals of the bicycle are attached to 100 turn coil of area 0.1 meter square. The coil rotates at half a revolution per second and it is placed in uniform magnetic field of 0.01 Tesla perpendicular to the axis of rotation of the coil. Find the maximum voltage generated in the coil. So, since here half a revolution per second, that represents number of revolutions in 1 second, that is half. That means frequency is produced there. So, since frequency is given, what is that voltage developed? That is always an AC voltage. AC voltage is usually represented by V equal to Vm sin omega t or E equal to Em sin omega t or E equal to E0 sin omega t. This represents the output of an AC generator. So, we have the output of AC generator E equal to E0 sin omega t. Okay. Here E0 represents the maximum voltage, or that is called peak voltage. Here we have to find out the maximum voltage, isn't it? So, maximum voltage or peak voltage is given by E0 equal to NBA omega. Okay, in AC generator we have discussed. So, the maximum voltage is given by E0 equal to NBA omega. What is N? Number of turns. Number of turns in the question it is given as 100 turns. Then magnetic field, what is the magnetic field here? Magnetic field is 0.01 Tesla, that is given. Area, that is also given 0.1 meter square. What is omega? We have omega equal to 2 pi nu, isn't it? Omega equal to 2 pi nu. That is 2 into 3.14 into what is the frequency given here? Frequency is half a revolution per second. Half a revolution per second means that is half a revolutions per, in 1 second how many revolutions are there? Half, that is 0.5. So 0.5 is frequency. Frequency means number of revolutions per second. Here half a revolution per second means what is the frequency here? 0.5. So all the values are directly given. Now we can substitute. The maximum voltage is N, that is 100. Magnetic field, that is 0.01. Area, that is 0.1 into omega. Omega is 2 into 3.14 into 0.5. Okay. Now if we substitute, the final answer is 0.314 volt. So the maximum voltage generated in the coil is 0.314 volt.